Okay, some of this is joint work with my PhD student, Ethan Schreiber. I'm not going to talk about, there's a paper in the proceedings which is the latest technical advances there. I'm not going to talk much about that. I'm going to give instead an overview of the problem, and I've been working on this off and on for probably about 20 years, and some of the work I'm going to talk about is almost 40 years old, so I'm going to give you, if you want to know the most recent technical advances, that's in the paper I'm going to talk about this more generally. I should start by saying this is an example of what Wheeler was railing against this morning. So an example of an old graybeard giving a talk about yet another optimal algorithm, still focused on that old stuff again still. So let's start with a very, very simple scheduling problem. And the motivation here is if you want to understand something, start with the simplest possible non-trivial example and see if you can understand that. And if so, then go on to things more complicated. So here's the scheduling problem. I give you n jobs. Each has a different time duration. I want to schedule them all on k identical machines. Each job has to be assigned to one machine. Machines can only do one job at a time. And I want to complete all the jobs as soon as possible, so I want to minimize the make span. Okay? It turns out this is NP complete with just two machines. Okay? So I can't think of anything simpler than this. There's no constraints. You just want to load balance a bunch of jobs on a bunch of identical machines. That's all we're going to do here. Wrong direction. Okay, so the corresponding abstract problem, and actually I have to thank Wheeler for introducing me to this problem almost 20 years ago when he was a student in my graduate class. The abstract problem is called number partitioning. I call it identical scheduling of machines because that's what the OR people call it literally. And this is a scheduling conference, so why not? But number partitioning is I give you a set of n integers which correspond to the time durations of the tasks. You want to assign each to one of k subsets, those are the machines, and you want to minimize the largest subset sum, which is the make span. Are there any questions about the problem? Because if I lose you here, I've lost you for good, that's for sure. Okay. So here's a very simple example. This is two-way partitioning. We'll talk first about two-way and then go on to multi-way. If I give you the numbers 4, 5, 6, 7, and 8, if I put 4, 5, and 6 in one subset and 7, 8 in the other, then the sum of the subset sums, they're both 15. And since they're perfectly balanced, that's obviously an optimal solution. You can't do any better. So we're going to start, as I said, with two-way partitioning and then move on to multi-way partitioning. Here's the simplest, most obvious greedy approximation you can think of for this problem. What you're going to do is you sort the numbers from in decreasing order. Everyone knows if you want to pack things like your suitcase, you put the big things in first, and then you fill in with the small things, and the whole is created by the big things. We're going to assign each number to the subset with the smallest sum so far. So if we start out with our numbers here, we're going to sort them now from largest to smallest. The 8 goes in one subset, the 7 goes in the other. Since 7 is smaller than 8, the 6 is going to go with the 7. 13 is greater than 8, so the 5 goes with the 8. And now each of these are the same, and so the 4 can go in either subset, and you end up with subset sums of 17 and 13, and the make span is 17. And so this is worse than the solution we had before, but this runs in only n log n time. Let me give you another very clever and elegant approximation algorithm due to Richard Korf and Randy Karmakar. This is called the KK algorithm. It's from 1986. I'm going to describe the algorithm first, and then tell you why it works. You sort the numbers in decreasing order first. Okay, we're going to take the two largest numbers, we're going to remove them from the set, but we're going to put back in their difference. So we're going to replace the two largest numbers with their difference. And we just keep doing that until there's only one number left. When we're all done, that last number is the difference of the final subset sums, and it corresponds to the, and then with a little extra work, some extra bookkeeping, we can actually construct the individual sets. And this also runs in n log n time. So the question is, why does this actually work? If you take two numbers and replace them by their difference, what you're doing is you're committing to putting those numbers in different subsets without deciding which number is going to go where. So if I put the 8 in the left subset, and put the 7 in the right subset, then that's equivalent to placing their difference of 1 in the left subset, because I can just subtract 7 from both sides and I get what's left over, the 1 in the left subset. If I move the 1 to the other subset, that's equivalent to swapping the numbers. So replacing two numbers by their difference basically says I'm going to separate them, but I'm not going to decide which one's actually going to go where. If you apply this algorithm to this particular problem, you get another solution which happens to be 7, 4, 5, and 8, 6, which have subset sums of 16 and 14, and a make span of 16. Better than the greedy algorithm, still not optimal. Okay? So now let's look at optimal solutions. And what we're going to do is we're going to take each of these greedy solutions and convert them into a complete algorithm, which is going to be optimal. So the complete greedy algorithm is probably the first thing you think of if you wanted a complete algorithm for this problem. What we do is we again sort the numbers in decreasing order, and then we're going to search a binary tree of depth n, where n is the number of integers. Each level of the tree corresponds to assigning a different number, and each node is going to either assign the next number to the left subset or the right subset, and it's going to put it in the smaller subset first. So the left branch is going to put it in the smaller subset. So the first solution you find is the greedy solution, and then the overall solution, the overall search is a depth first branching down of this binary tree. There's some pruning that you can do to make this more efficient, which I won't go into. And this gives you an optimal solution. It's the first thing you'd think of if someone told you on a problem set to solve this thing completely. That's what you would do. We can also convert the Karp algorithm into a complete algorithm. Remember what KK does is it takes the two largest numbers and replaces them by their difference. The only other thing you can do, the only other option is to place them in the same subset. And that corresponds to replacing them with their sum. If you can put two numbers in the same subset and keep them together, you can just replace them by their sum. So the complete KK algorithm, or CKK for short, searches a binary tree. The left branch replaces the two largest numbers with their difference, and the right branch replaces them by their sum. And this also gives you a complete algorithm for the problem. It turns out that two-way partitioning is actually a special case of a problem called the subset sum problem. So subset sum is, given a set of numbers, find a subset of those numbers whose sum is closest to a particular target value. That's the general subset sum problem. If I want to use this to solve number partitioning, what I do is number partitioning, two-way partitioning, is equivalent to a subset sum problem. It's a special case where I pick the target value to be half the sum of all the numbers. So if I pick the target value to be half all the numbers, the sum of them all, then finding a subset sum whose subset whose sum is closest to half is equivalent to finding the best two-way partition. Here's an algorithm due to, I promise you will work, this almost 4 years old, due to Horowitz and Sani from 1974 for solving the subset sum problem. I'm not going to go into details, but it's a subset sum algorithm. For n numbers, the time complexity and also the space complexity are 2 to the n over 2. So this is a lot faster than CGA and CKK, the complete greedy algorithm, and the complete Karp algorithm, which run in 2 to the n time. But it takes 2 to the n over 2 space as well, whereas CKK and CGA and CKK take linear time. But this is a lot faster than these other two algorithms. It turns out that in 1981, Schroppel and Shamir improved on the Horowitz and Sani algorithm, generalized it somewhat. The time complexity for the SS algorithm, which is Schroppel and Shamir, is also 2 to the n over 2, but it runs a lot faster in practice than the Horowitz and Sani algorithm. Its main advantage, however, is the space complexity is only 2 to the n over 4. This means it's practical for up to about 100 numbers, but this 2 to the n over 4 space complexity is the big win here. And you can also extend this algorithm. Strictly speaking, their algorithm only finds a subset sum whose sum is closest to a target value. You can extend this to find all subsets that are within a given range. So you give an upper and lower bound, and then you can use an extended vergence algorithm to find all the subsets in that particular range. Dynamic programming. This algorithm, number partitioning, is known as pseudo-polynomial, or weakly NP-complete, which suggests that it's not as hard as strongly incomplete problems. There's a dynamic programming algorithm, again I won't go into the details, it's in Barry and Johnson. It runs in polynomial time for fixed size numbers, so that looks attractive. However, the memory required is proportional to half the sum of all the numbers. So if you have numbers of high precision, very large numbers, it's really not practical. In fact, this is only practical for two-way partitioning of relatively small numbers. And surprisingly, this is actually a negative result, which is in the paper. It turns out, experimentally, dynamic programming is actually slower than CKK, which only requires linear space. And so it's really kind of a dog compared to a much simpler algorithm. So we're not going to say too much more, but it's worth mentioning it because it's certainly a possible algorithm you can implement. Another feature of this problem, and this will be familiar to people who do CSPs probably, is this easy, complexity transition. So if you hold fixed the number of subsets k and the size of the numbers, as n increases the number of numbers, the problems initially get harder, and then at some point they get easier and eventually become trivial. So we have this easy, hard, easy as n increases. Now the reason for that is due to the presence of what are called perfect partitions. What do I mean by that? If all of the subsets have the same sum, we've got a perfect balancing, and the partition is clearly perfect. Okay, so if the sum of all the numbers is divisible by k, perfect partition has subsets all of which have exactly the same value. If it's not divisible, if the sum of all the numbers is not divisible by the number of subsets, then a perfect partition will have subsets whose sum differ by at most 1. Okay? The virtue of perfect partitions is once you find a perfect partition, you can stop searching immediately. You don't have to keep looking for better because you know you've got a perfect partition, you know it's optimal, and you can quit. And that's what makes these problems easier. So what happens is, as n increases, perfect partitions become more common. And the reason is the following. It's sort of a pigeonhole problem. The number of pigeonholes is the number of pigeons is the number of different partitions. And if k is the number of subsets, the number of different partitions grows as k to the n. It's exponential. The number of different subset sums, which is pigeonholes, grows only linearly with n. So we've got an exponential number of pigeons, and we've got a linear number of pigeonholes. So when n is large, you've got a lot more pigeons than pigeonholes. And so what happens is those holes get very crowded, including the one which corresponds to the perfect partition. So as n gets large, perfect partitions become much more common, and as they become more common, the problems get a lot easier. And that's the reason for the easy, hard, easy complexity transition. So for two-way partitioning, the best algorithms are the following. If n is small, CKK turns out to be the fastest. This is the complete Korf algorithm. It's faster than the complete greedy algorithm for two-way partitioning. For larger n, if there's no perfect partitions, then Truffle and Shamir is the fastest algorithm. If there's lots of perfect partitions, then CKK is still the fastest algorithm, even for larger values of n. And for n greater than 100, Truffle and Shamir is really not feasible, and then CKK becomes the best choice for those problems. Multi-way partitions, that's two ways. Now let's talk about multi-way partitioning a little bit. All three of CGA, the complete greedy algorithm, the complete Korf algorithm, the dynamic programming algorithm, all generalize to multi-way partitioning. The complete greedy algorithm dominates both the complete Korf algorithm and dynamic programming for multi-way partitioning. Now I'm going to describe two other algorithms for multi-way partitioning. First one's called recursive number partitioning. The idea behind this is if I give you an optimal multi-way partition, by multi-way I mean more than two subsets, if you take any subgroup of the subsets and optimally partition the numbers in that subgroup, you still have an optimal multi-way partition, because if I take a subgroup of the subsets and optimally partition, the only thing I can do is lower their maximum subset sum. So I can't make the solution worse. So given an optimal partition, optimally partitioning a subgroup of the subsets leaves still an optimal partition. Okay? So here's how three-way recursive number partitioning works. We generate, using the extension of the Stroppel and Shamir algorithm I mentioned, all possible first subsets of the three that could be part of a partition that's better than the best so far. How do we know it can be better? Well, first of all, it has to have a subset sum, which is better than the best maximum subset sum. It also has to be large enough that what's left over could possibly be partitioned two ways, where both of those are better than the best so far. So for each of those subsets, which could be part of a better partition, we recursively and optimally partition the remaining numbers two ways and see if we've got a better solution than we started with, okay, than the best we have so far. Let's skip these two in the interest of time. Let me describe the more general overall recursive number partitioning algorithm. So the first thing we do is we run the KK, the Korf approximation algorithm, to get an initial solution, and we set the initial down to m. So m is the maximum subset sum of the best solution we found so far, the make span, if you will. Then we use an extension of the SS algorithm to generate all two-way top-level partitions that could lead to a better k-way partition. So if we're doing three-way partitioning, we divide them into a single subset and a set of numbers that will be partitioned two ways. If we're doing four-way partitioning, we divide the numbers into two groups, such that each group will then be partitioned two ways. If we're doing five-way partitioning, we divide them into a group that will be partitioned two ways, and the remaining numbers which will be partitioned three ways, etc. So we generate all the possible top-level two-way partitions that could lead to a better k-way partition. That's based simply on the bounds of subset sums. For each of those top-level partitions, we recursively partition one of the, quote, half subsets. If the subset sums in that half are all less than m, the best we've had so far, then we recursively partition the other half subset. And if the complete partition is better than the best so far, we update the best solution so far. So it's a recursive, top-down sort of algorithm. You partition things and then keep sub-partitioning them. And you keep track of the best bound you found, so the best solution you found so far. And this turns out to be a complete algorithm. Now I'm going to switch gears a little bit to a closely related problem, which most of you are probably familiar with, which is called bin packing. Okay? So bin packing says given a set of integers and a fixed bin capacity C, assign each integer to a bin so that the sum of the integers assigned to each bin doesn't exceed the capacity C. And you want to do this so that you minimize the number of bins needed. If you think of this as a scheduling problem, this corresponds to minimizing the number of machines you need to complete all tasks within a given amount of time. So it's closely related to our number partitioning problem. Okay, so for number partitioning, we fix the number of bins or machines, and we want to minimize the needed capacity or the time to complete all the tasks. For bin packing, we fix the bin capacity, which is the make span or the time to complete them all. We want to minimize the number of bins or the number of machines. So these are very closely related problems, and it turns out, given an algorithm for either of these problems, you can use it to solve the other problem. And I'll show you how to do it in one way, and we'll leave unsaid how you do it the other way. It turns out to be pretty straightforward as well. So here's how you solve number partitioning with bin packing. This goes back to Kaufman, Gary, and Johnson from 1978. So what we're doing is we're trying to solve a number partitioning problem, but we're using bin packing as the method to do it. So we fix the number of bins at k, which is determined by the number partitioning problem. And we're looking for the smallest feasible bin capacity. By feasible bin capacity is a bin capacity which will contain all of the numbers within that within k bins. We're going to use a greedy algorithm like first fit decreasing or best fit decreasing to get an upper bound on the bin capacity. Lower bound's easy. You sum all the numbers and you divide by k and you round up. That gives you a lower bound on the bin capacity. So now we have a range of bin capacities. What we're going to do is we're going to do a binary search over that range of bin capacity. So for each probe into there, we'll pick an initial bin capacity halfway between the upper and lower bound. And we'll use any of our favorite bin packing algorithms to try to pack all the numbers into those k bins using that bin capacity. If we're successful, then we'll reduce the bin capacity to half the remaining. If we're unsuccessful, we'll increase the bin capacity. Okay? So this is the technique that's primarily been used in the R community for solving number partitioning. They use bin packing, and then they use a particular bin packing algorithm, basically a branch and cut and price integer linear programming model to do that. Okay. So the next question is, what's the best algorithm for multi-way partitioning? Well, it turns out it depends. Okay. The undominated algorithms to consider are the complete greedy algorithm, recursive number partitioning, and bin packing. For small values of n, okay, like a dozen or so, the complete greedy algorithm is the fastest because its overhead is very low. If you want to partition 7 or more ways, it turns out bin packing is fastest, okay, so far. And for partitioning 3, 4, or 5 ways, RNP, recursive number partitioning, appears fastest. And by the way, these are not small differences. We're talking about orders of magnitude. So if you pick the wrong algorithm here, it's not like you're going to be twice as fast or 3 times. You could be several orders of magnitude off of what the best algorithm is. So these differences are really enormous. And this is assuming here very large numbers without perfect partition. So to do these experiments, we use 48-bit numbers. So these are very large numbers. There's no perfect partitions. And these are sort of the results that we get. 6 is kind of the break-even point. In practice, however, this can be a little bit of a defense of optimal solutions. It turns out that if we hold the size of the numbers fixed, okay, as n increases, as I mentioned before, the problems eventually get easier due to the presence of perfect partitions. Okay, so in one set of experiments, we fix the size of the numbers. We use 31-bit random numbers. Okay, so to give you an idea of what sort of precision that is, 31-bit integers. If I take those numbers and consider them time represented in seconds, with 31 bits, I can represent 68 years. So the kind of precision we're talking about here is a precision of about 1 second in 68 years, which intuitively seems like pretty good precision for most practical problems. So if you fix your precision at 31-bit numbers, you can recursive number partition turns out to be the best choice here for these small values, and you can optimally solve arbitrarily large 2, 3, and 4-way partitioning problems in less than a minute on average. And the small ones you can solve because they're small. The big ones you can solve fast because there happen to be perfect partitions and they get solved very quickly. And the hardest ones are in between, maybe 50 or so numbers. So this is a case where, in practice, even though the problem's NP-complete, if we fix the precision to something reasonable, you can actually solve arbitrarily large numbers, arbitrarily large instances in practice very fast. In fact, this less than a minute is for the 4-way partitioning. It's faster for the 3-way and faster for the 2-way. Generally, it gets more difficult as the number of subsets increases. So Chris is waving me down here. So here's the take-home message. If you don't care about this problem, why should you care about the talk? And here's my suggestion. you'd expect that for an algorithm, a problem that's this simple, subset sum, number partitioning, even bin packing, okay? For such a simple scheduling problem, you'd figure there would be, it's been around for a very long time, 50 years or so, you'd expect that there would be a simple algorithm, and that would be the best you could do, and that would be the end of the story. For example, graph search kind of has this flavor to it. If you're trying to find the shortest path in the graph, basically you want to do A star, possibly you're deepening A star, but probably A star, depending on your problem. And that's about all you can say about finding optimal solutions. One reason that finding optimal solutions on some of those problems is not so popular anymore, because it turns out to be harder to come up with new ideas, because we've got a very simple algorithm we need and show that is optimal. And so you expect a similar thing to happen here, but it doesn't, right? So we're still finding new methods, okay, which give us, new bin packing algorithms, new number partitioning algorithms, which gives orders of magnitude improvement, okay? And the best algorithm, actually, if you take the entire problem space, it actually has 3 dimensions that are relevant. N is the number of integers, K is the number of subsets, and then the third dimension is the precision of those numbers. Depending upon where you are in that 3-dimensional space, a different algorithm may be the best choice. And again, the differences can be orders of magnitude. So what that says is that if we're still making pretty dramatic progress on such a simple problem, there's kind of a couple ways of looking at it. The sort of positive way of looking at this is there must be great potential for improved performance of much more complex scheduling problems, okay? The other way of looking at it, the negative way, is we probably don't know a whole lot about scheduling problems, or at least optimal solutions, if we're making this kind of progress and still can't figure out exactly what's the best algorithm to use in every case and exactly why on such a simple problem, that I think there's a lot more that can be done in terms of understanding more complex problems. So that's what I had, and I want to thank you for your attention, and if we have a little bit of time, I'd be happy to take questions.